Good morning. Okay, we'll get underway. Got a lot to do. We're working on finding electric potential due to charge distributions. And so what we found last time was that we went inside of a charge distribution where there was no electric field, and we saw that the delta V had to be constant inside of that charge distribution because there was no electric field there. So remember, delta V is negative integral E dot ds. So when E is 0, delta V has to be 0, not V. So inside a conductor, for sure, we know E is 0 when the conductor is in electrostatic equilibrium, but any place the electric field is 0, delta V equals 0, but V does not have to be 0. It can be. Okay, so inside of a conductor or any region where the electric field is 0, delta V has to be 0. That means V has to be a constant. It might be 0. 0 is a constant, right? But it doesn't have to be 0. It has to be whatever it was when you entered that region, right? Whatever that border is. We always make it continuous. Okay. All right, so let's take a look at just a little warm up here. If our electric field is uniform, then that integral becomes really easy, right? Integral of E dot ds just becomes E times the distance, right? I'm using D for distance. Should I use S? So let's take a look at our parallel plate example. We'll have our positive plate over here. These are infinite sheets. So we have a nice uniform electric field. And let's just pick one. If I told you that this was V equals 0, the negative plate was V equals 0, what would the other plate be? Positive or negative? Has to be positive. Okay. Now, because the electric field always points toward lower electric potential. So if I know my electric field is pointing in this direction, then whatever is in that direction has to be a lower potential than before. So if I end up at 0 over here, and the electric field points toward lower electric potential, then I have to be above 0. I have to be something greater than 0, which is a positive number. So now I don't have to define it this way though. I could take those same two parallel plates. I could take that exact same configuration and I could tell you that this is V equals 0 over here. So what's the other plate? So this one would have to be negative V naught then, right? Where V naught is E times D. Or I could have done it this way, right? Then what's the positive plate? What's the negative plate? Okay, plus V naught over 2 minus V naught over 2, right? If this is halfway in between, right? Okay, we're warmed up now. Ready for a real problem? Okay, so we've got a solid insulating sphere. Uniform charge density throughout its volume. And we'll have radius r, total charge, capital Q. We'll make it positive charge. Okay, so what do we want to do? Find E and V everywhere, given V equals 0 at R equals infinity. Okay. So what is this? This is a typical Gauss's law problem to find electric field, right? Because it's spherically symmetric. And we know that integrating over a volume, integrating over a three-dimensional charge distribution to find the electric potential is very difficult. So chances are that's not the best approach to use. The best approach is to find the electric field everywhere using Gauss's law, and then integrate the electric field, negative integral E dot ds, to find your electric potential. Okay, so you've got to spot those problems, be able to see a problem like this and spot how to solve it. Okay, so find the electric field everywhere. We'll do the easy one first. Find the electric field outside of the charge distribution. Have you done that already? Okay, now you have, right? What's the electric field look like outside of a spherically symmetric charge distribution? A point charge. We can put all, if we're outside of a spherically symmetric charge distribution, it looks like a point charge. We can take all that charge and just put it at the origin. So what's the electric field from a point charge? K Q over R squared. And it's positive charge, so it points radially outward. I will call that the R hat direction, outward. So I'm done with this region, right? I've got the electric field at any position R from the center of this charge distribution. Now we have to find the electric field inside the charge distribution. Okay, so we've got a charge distribution. We're going to draw our Gaussian surface inside here somewhere, right? And we'll use Gauss's law. The integral of E dot dA over the whole surface of that Gaussian sphere is Q inside over our constant epsilon naught. And of course, because we have this nice symmetry, the electric field is constant everywhere over the surface of that Gaussian at that given radius, right? So this is just E times the surface area. And what is the surface area of a sphere? 4 pi r squared. Now all we need to do is figure out how much of that charge is inside of the red Gaussian sphere that I drew. We know the total charge is capital Q. So I need to find, or it's however you like to think of it. You can take a ratio of the volumes, multiply it by the total charge. You can first find the charge density and multiply that by the volume of your Gaussian. It's the same equation either way. But you end up with the volume inside times Q total over V total, right? Now we plug this in for Q in, this is just, we found Q in there, right? So we're at E times 4 pi r squared is r cubed Q over capital R cubed. Can we use Gauss? This is Gauss's law. Qn equals Vn. Qn is Vn times the density. Right? This is the density here. Qn, let me add it here, hold on. This is just, this doesn't have anything to do with Gauss's law. It's just a definition, right? The density, the charge density is the charge per unit volume of our three-dimensional charge distribution, right? If it was just a surface with charge on it, we would say the total charge on our surface is the surface area times sigma, right? And if it was a line charge, we would say our total charge is the length, S, times lambda, the charge per unit length, right? So this one is a volume. Charge is spread out over a volume. So we use our rho, our charge per unit volume. It's just a definition of charge density, I think. Okay, so figure out Q in however you like to think about it, but it's basically you're taking the ratio of the volumes and multiplying by the total charge, or you're just using the charge density. It's the same either way. Now, when you bring this down, right, when you bring the 4 pi r squared to the other side, you see that this r cubed just becomes an r. So I have my electric field is, what do I have, a 1 over 4 pi epsilon naught. That's my constant. I have a Q over capital R cubed, and I have a little r. So E is some constant times R. E is linear, increases linearly with R when you're inside of the charge distribution. So if I were to plot the electric field, here's my charge distribution. Here's my E field plot. That's the radius, right? What does it do? It increases linearly as I start at the origin, right? It has to be 0 at the center. When R equals 0, the E field has to be 0 because you have equal charge on every side of you, creating an electric field that's canceling out. And then as you go outside, it just drops off 1 over R squared like any point charge would. It's not a very good smooth curve, is it? Something like that, right? E proportional 1 over R squared in this region, E proportional to R in this region. Okay, so we've got E everywhere now. So we're ready to start the real part of this problem, which is finding the electric potential. Okay. Now, where do we start? we're going to use this equation, delta V minus the integral E dot ds. This gives us a change in voltage. Well, that doesn't really help us unless we know what one of the voltages is. So if we start where we know what the voltage is, then when we find the change, we're really finding the voltage at the next place because we know where it is where we started. So this is if only really helps us find the potential everywhere if we start where we know what the potential is. And in this case, that's at infinity. At infinity. So I'm just going to do this. I'm just going to walk through it. But I kind of know what the answer has to be, right? Because when we're outside of a spherically symmetric charge distribution, what does it look like? It looks like a point charge at the origin, right? And what's the electric potential due to a point charge? K Q over R. So we know the answer has to be KQ over R, but I'm going to go ahead and walk through the steps because sometimes it's not obvious what the answer is, and we want to walk through the steps to solve the problem. In this case, it happened to be simple, right? But let's walk through it and learn the procedure for cases where it might not be as simple. So we want to do this. Integral. So we've got a charge distribution here. Okay, and maybe I'll put the plus Q. Yeah, and we want to go from infinity out here. This is R equals infinity. We want to go from infinity as our initial point in to some point which is just any arbitrary R, right? We're going from an initial place to a final place. And this is just R. This is just some arbitrary R. So R final is just any arbitrary R, and R initial is infinity. Okay? We're starting at infinity, and we're moving in just to any arbitrary R around our charge distribution. So let's set up our integral. Delta V minus the integral E dot ds. Okay, so what does delta V mean? It means V final minus V initial, right? Delta is always final minus initial. Minus the integral. Now we can plug in our E. We know what E is outside of this charge distribution. This is, I should put over, this is for R greater than the radius, right? Question, could we have V initial be the voltage on the sphere and V final be 0 at infinity? Well, then you're ignoring everything in between, right? Then you'd know what the voltage is here versus 0, but you wouldn't know what the voltage is anywhere in between, right? The question is to find the electric potential everywhere. So we need to start where we know what it is, which is infinity, and then move into any arbitrary R. This will give us V as a function of R. So it'll tell us V anywhere between the radius of our charge distribution and infinity. Our next exam is Friday, and I will send out some instructions this afternoon, okay? So how to log in and things like that. And I'm hoping you're all available 15 minutes earlier. I'd like to start the exam 15 minutes earlier to give you a little extra time so you're not as crunched for time. Okay. I'll send all that information out this afternoon, though. Office hours 4 to 5 every day. Okay. Delta V, V final minus V initial. We got our minus sign. Integral, E dot ds. Well, we know what E is out there. E is KQ over R squared. ds is just dr, right? We're moving along the radial direction here. Now, the dot product, how do I deal with that dot product? So my ds is this direction. The electric field points this direction. So the dot product gives me a cosine 180 because the electric field and the dr are, when you put their tails together, you get an angle of 180 degrees. And then my limits of integration are always from the small number to the large number. So this would be R final to R initial, because initial is bigger than final. So I believe that's how you set up this integral. We'll find out very shortly if I screwed up a minus sign, and we'll fix it, right? I try, like I said, I try to get my minus signs right, but it's tricky getting the limits of integration correct, getting all the minus signs correct, getting the cosine correct for the dot product. You might miss one somewhere. At the end, it's so easy just to check and make sure the answer is correct and fix it if it isn't. Okay, so what is V final minus V initial? That is V at any R, right? V at R minus V at infinity. That's where I started. And V at infinity is what? 0. That's, we know, yes. We know it's 0 there. So, so then I just have V at any R is going to be, what is it going to be? A minus, and a minus is a plus. I've got a K, a Q, an integral of dr over R squared from R to infinity, right? And so what do I end up with here? I got a KQ a negative 1 over R from R to infinity. That's 0 minus becomes plus 1 over R. So it looks correct because I knew what the answer had to be, right? I knew it had to be KQ over R, and it looks correct. I got KQ over R, but let's check the sign, make sure we got all those minus signs right, okay? So V is 0 at infinity, right? V is 0 here, and the electric field points in that direction. Electric field always points toward lower potential. So what does the electric field have to be at any place before we get to infinity? Has to be bigger than 0, has to be positive. So my answer here has to be positive. This number must be positive. And what did I get? I got a positive number, right? Okay, so the signs work. and we got the value we expected, kq over r, just like a point charge. Okay, so this is dr points the direction we're going. So we're going, we started at infinity and we're working our way in towards some other location. So dr points in that direction, the direction we're going. E points radially outward. So that's where that came from. The minus sign canceled, but this is -1, this is -1, they canceled. Okay. All right, so now we know the electric potential anywhere from infinity into the radius of our spherical charge distribution. But we want to go inside. So we say V at R equals the radius is KQ over capital R, right? We just plug in. We can go all the way up to the boundary of our charge distribution. So that's what the potential is at the boundary of our charge distribution. Now we want to go inside. That's an R. So the electric field is different inside, so I have to start over again, right? Anytime the electric field changes, I have to stop at that boundary and start again, do it like it's a whole new problem. So I say delta V, here, let me draw what we're doing here. We have a charge distribution. We're going to start here. This is our initial. We're going to end up at any arbitrary R. We're going in this direction, right? And this is any arbitrary R, R final. So R initial is the radius, and R final is any arbitrary R inside of this charge distribution. Limits of integration. Question about limits. Limits of integration are always, if I understand math correctly, always the smaller number at the bottom and the bigger number at the top. The cosine 180 tells you that you're going in the opposite direction. Don't double count. See, I told you, it's very tricky to get these minus signs right. Very tricky to get all the minus signs right. Try to get them all right. And then at the end, make sure you got them right. Make sure it makes sense. Fix it if you didn't. Okay. Why is one of them infinity? Because you always start where you know what the potential is. And in this problem, we were given that V equals 0 at infinity. So we started at our initial is infinity. And then when we integrated, that our initial became infinity, right? That's where we start. If we were given that the electric field, the electric potential was some value at R equals R, V equals 10 volts or something, if that's what was given, then we would have started our integral here and integrated out from there. You always start where you know what the potential is. In this case, it was 0 at infinity, which is typically the case with spherical charge distributions. With cylindrical charge distributions, we usually set the potential to be 0 at the surface of one of our cylinders. No, you can't just make it up. You have to be given one of the potentials. Otherwise, everybody could have a different answer. Right? You might define 0 to be infinity. I might define 0 to be somewhere else, somebody else, 0. So we could all have the same delta V's everywhere, but different answers. Everybody's would be shifted by some constant from everybody else's, right? Kind of like up here with this situation, right? One person defines the potential to be 0 here, the other person defines it here, somebody else defines it in the middle. We all get the same delta V, right? But we all have different answers for the electric potential everywhere. So in order to get everyone to have the same answer, we'd have to be told some reference point. The potential is 0 here. Then we all get the same, we work out from there, we all get the same delta V's, so we could find the potential everywhere. And like I said, for spherical, yeah, this was stated in the problem, yes. Where was it? Here. So for spherical charge distributions, it is almost always stated to be 0 at infinity. And for cylindrical, almost always on the surface of one of the cylinders, because you end up with an ln of r over the radius of the cylinder. So it naturally goes to 0 there. Usually we pick points where mathematically it would naturally go to 0. That's kind of what makes sense. But you don't have to, I guess. The bounds of the integral are always from a small number to a large number. So we're integrating r. So we put the small r in as the lower bound here, right? Is this what we're talking about? Our final was, we started out at infinity and we're working our way into our charge distribution. So our final is a smaller number than our initial. Our initial is infinity, right? So any other position is going to be less than that. So we start with a small value and go to a big value. Okay. Okay, so we picked places where the function naturally goes to 0, typically. Good. Now we're ready to go inside our charge distribution. So this is our picture. We're going to start where we know what the potential is. That's at the surface. It's this value right here, right? That's what the potential is at the surface. We'll start there. We know what the electric field is inside this region, so we can use our function delta V is minus integral E dot ds. So this is going to be V final minus V initial. Our electric field was, what was it? It was K, electric field, here it is. There's the electric field. KQ over capital R cubed times lowercase r. So that's our electric field. And our cosine, again, is a 180. Because we are going in, right? Our dr is in, and our electric field is out. The cosine comes from the dot product, right? So this is my E, and my ds, and there's a dot product in between them, right? So the dot product gives us the cosine 180. Okay, so there is. We got these constants. We've got an r, dr, and a -1. Oh, limits of integration. We're going from, this is going to be r final is the smaller number, to r initial. And r initial we know is capital R. And r final is any r. So let's go ahead and plug in what we know here. So what is this? This is going to be v at any r minus v at the boundary of our charge distribution, capital R. And that has to equal negative and a negative become a positive. I've got a k q over r cubed. Those are just positive constants. I have an integral of r dr from r to capital R. So let's finish the right side of this equation, and then we'll check our signs. So this is going to be kq over r. That's just our constant. This is r squared over 2, evaluated from r to capital R. I'm just trying to go through and show you every step in the process, right? It's R initial to R final, but we know what R initial and R final are for this problem, right? Those change. You're always worried about where initial and final, right? We're going to start at some initial place. It has an initial potential there, V initial. It has an initial location, R initial. We're ending up at some final place. It has a final potential and a final position, R final and V final. But if we know what they are, then we'll plug them in when we know what they are. I'm just trying to write out every step in the process for you. So what do we get here? We get a constant, capital R squared over 2 minus R squared over 2. Okay, let's check our signs. All right, so what is this one? Positive or negative? Positive, because the electric field points outward from final to initial. So the initial has to be less than the final. So our delta V has to be positive. This is just a bunch of positive constants, right? This is positive. And this has to be positive because little r is smaller than capital R, right? We're inside, right? So we're good. Everything checks. If we weren't, you just throw a minus sign there, right? And fix it, right? But we're good. We don't need that. Okay. So now let's finish. Oops, what happened to my, I hate when stuff disappears like this. There we go. Okay, now let's finish the problem. So what's the next step? Let's plug in things that we know, okay? So we're trying to solve for V at any R. So let's let's get that by itself on the left side of the equation. And we'll move V capital R over to the other side. So we have a KQ over R cubed. I guess I could pull that 2 out. Why don't I just pull that 2 out so I don't have to deal with it anymore? 2. And then I've got a plus VR. I just moved the V at capital R over to the other side, but I know what that is, so I can plug in what I know. That's why we always start where we know the potential. So let's plug that in. We know the potential there. So this is KQ2R cubed. And that was, what was that? It was KQ over capital R, right? So there's our answer. For V, for R greater than, sorry, R less than the radius of our charge distribution, this is what we get. And our answer for the previous question was right here. Capital R cubed comes from Q inside. Right up here, where are we? Right here. So we were using Gauss's law to find the electric field inside of that charge distribution. And it depended on Q in. And Q in is the density, which is the total charge over the total volume. So you get the radius cubed of the total of charge distribution, capital R cubed in there. Got it. Okay. Now, we could plot this if we wanted to. This is a tricky one to plot. There's our charge distribution. Here's our electric potential. So we know what it is outside the charge distribution, right? If we go outside the charge distribution, it starts at the surface. At the surface, it starts KQ over capital R. That's what it is at the surface. And it drops off as 1 over R as you move away, right? V proportional to 1 over R. But then inside, it has this odd, it goes as negative R squared, negative R squared. So it does this. So in this region, it's proportional negative R squared. And what is it at R equals 0? Plug in R equals 0, and we get 3 halves KQ over R. 3 halves KQ over R at this point. And so it looks something like that. It always ends up being continuous because of the way we link, right? Every time we get to a boundary, it's linked to the previous boundary. Remember here we had this R squared. Why does it disappear? We had this V sub R here, and we move it over to the other side, and that makes it continuous. These electric potential functions should always be continuous through all your boundaries. Okay. All right, this is a good place for a 10-minute break. Let's do that. You just plug in 0. Plug in 0 for little r and figure out what the potential is, and that's what it turns out to be. Okay, I'll pause the recording. Okay. Chapters covered on the midterm. What's it say on the calendar? I think it says 5 through 7. Does that sound right? Yeah. So for chapter 5, I'm not going to ask you anything specific to chapter 5. I don't think it's the techniques we used in chapter 5 are the same techniques you're using in chapter 7 to find the potential due to a charge distribution. So that's the connection there. Chapter 6, definitely you have to know all of that because you need, like we just did, right? You had to find the electric field due to some charge distribution using Gauss's law in order to do the electric potential using delta V equals negative the integral of E dot ds. So, so that one definitely you're going to need to use Gauss's law to find electric fields due to charge distributions that have those symmetries. Omit 5 point. That means don't worry about what's in 5.7. I don't know what that is offhand, but okay. So let's see. Excuse me. Okay. So I've got this worksheet here. Should we do the worksheet now? Let's do that. Then I don't have to move it anymore. Okay, so let's do this. We're given this situation. We've got these equipotential surfaces. Dashed lines represent equipotential surfaces. They're labeled. The circles are just there so you can judge distances. And various points are labeled A, B, C, D, etc. So what we want to do, we want to move a positive charge. Is that what it says? Yeah. From point P at the center to each of these other locations. And they want you to rank the work done. Well, we'll just find the work done for a couple of the cases. So let's move from point P to point A. From P to A, you're going to move a positive charge. And we want to know how would you find the work done by an external force in moving that positive charge from P to A if it starts and ends at the same speed? What does it say up here? It starts and ends at rest. question about the previous problem, why was the potential at the surface equal to the equation of a point charge? Because anytime you are outside of a spherically symmetric charge distribution, you can just treat it like a point charge at the origin. It's just the math works out that way. It worked out that way for gravity. It works out that way for electric forces and fields. And it also works for cylindrical charge distributions. Excuse me. If you're outside of some kind of a cylindrical charge distribution and it's symmetric about the axis of symmetry, the axis of the cylinder, I should say, if it's symmetrically distributed about that axis, then it looks like a line charge. You could take that cylindrical charge distribution and just put all of it at a single line charge at the center, and it's the same, acts the same way when you're outside. Okay, back to our equipotential surfaces here. So we want to find the work done by an external force in moving a particle from P to A if the particle starts and ends at rest, and we'll just call it Q, particle of charge Q. So your answer will be in terms of Q. So one of the things here is that it's oftentimes when we move charges, we think half the time we think about the field moving the charge and half the time we think about an external force moving the charge, right? Because the field might not make it go in that direction, we want to move it. So it takes an external force. So what we usually say is that the particle starts and ends at the same speed. If it starts and ends at the same speed, there's no change in kinetic energy. So the work done by the field and the work done by some external force have to be the same. Let's just take a quick example here. We have an electric field in some region of space, and we want to move a particle from whatever, A to B. Let's make it a positive charge. So we're moving a positive charge from A to B. If we let go of a positive charge at point A, what would happen to it? The field would push it to point B, right? Because the field, the positive charge moves in the direction of an electric field. So the field is positive. If we want it to start and end at the same speed, we have to reach in with some external force and slow it down, exert a force in the opposite direction and slow it down. So if okay, so if it starts and ends at the same speed, we have to, whatever work the field does getting the particle to move faster, the external force would have to come in and slow it down and get it to move slower to be at the same speed. Why do we like to think in terms of a field force and an external force? Because the particle doesn't always want to go in that direction. What if the particle was negative? Now we're moving a negative q. Okay, so if we let go of a negative charge at point A, is it ever going to end up at point B because of the field pushing on it? No, it's going to go the opposite direction. How do we get it to go from point A to point B? We have to reach in with some external force and push it that way to get it to go to B. And if we want it to end at the same speed, if we come in and start pushing on it, it's going to start moving faster and faster because we're pushing on it. But the field is pushing in the opposite direction. So if we push just right, then the work done by our external force equals the work done by the field. The particle stays at the same speed the whole time. So that's why, half the time when we talk about moving particles around, yeah, the field would push it in that direction. Half the time it wouldn't. We'd have to come in and push it in the to make it go in that direction with some external force. So that's why we sort of always have in the back of our mind that there are these two forces. The field is making it go one direction, and an external force comes in and either keeps it from accelerating, right? Keeps it moving at constant speed, or gets it to move in the other direction. So in this problem, they're asking for in this problem, they're asking for the work done by the external force. So what would happen here? If you let go of a positive charge at point P, is it naturally going to go to point A due to the field? Or do we have to push it? We have to push it. So if point A is over here and point P is over here, kind of, sort of, our electric field points from A to P, roughly. How do we know? Because A is at higher potential. A is at 30 volts. And the potential at P is 20 volts. And the electric field always points toward lower electric potential. So at least some component of our electric field has to be pointing from A to P. It may not be exactly like this, but at least some component of the electric field has to point from A to P. And if we release a positive charge here, how's it going to get to A? Well, the electric field is pushing it the opposite direction. So we would have to come in with some external force in order to make it go to A. So the work done by the external force is what? Positive, right? We have to push it in the same direction it's moving. The work done by the field then is negative. And what do we know about work done? Work done is Q delta V. And the reason I always write it like this is because some textbooks, it's the work done by the external force, some it's the work done by the field, and so some have a minus sign, some don't have a minus sign. But I always like to remember it this way, and then I just use this to get the sign right? So I know my sign already before I even figure out the magnitude. So this is just going to be 10 Q times 10 volts, right? 10 Q. And so if it's the work done by the external force, it's positive 10 Q. And if it's the work done by the field, that says field, it's negative 10Q. Okay. Let's do another one. Let's do B. Moving from P to B. Let's go back. Where is it? There we go. The question is, we're kind of ignoring the question. I'm asking my own questions. The question is asking you to rank the work done by the external force in going to each, from P to each of these other places, 6 other locations. I'm just saying we're just going to do a few of them. We're not going to do all 6. We'll do 3 of them. And we're just going to go ahead and calculate both external force and external work done and work done by the field. Okay, so B, point B, you're ready? So B is at minus 20 volts. P is at plus 20 volts. So what direction is our electric field? Basically from P to B, right? Electric field points toward lower electric potential. If there's one thing you remember from this class, let it be that. Okay, so that means if we release a positive charge at point P, the field is actually going to push it in that direction. The field is doing positive work. And if we wanted to stop at the same speed or end at the same speed it started with, we would have to reach in and slow it down and do some negative work. And what is the value of the work done? The work done is going to be Q delta V. And so delta V is 40. So the external force minus 40Q, and the field plus 40Q. So you're getting the feel for how you'd find work done moving particles around. Find delta V, multiply it by the charge you're moving. Don't worry about signs initially. Just find the magnitude, take the absolute value. And then in the end, just think about, does it have to be positive or negative? Should we do one more? P to E.
Hey, Professor, I have a question.
Yeah.
So the work done by field and the external equals 0. Is that right? The total, is that what we should use here to calculate?
Yes, if the particle starts and ends at the same speed.
Okay. Oh, I didn't see the same speed.
Yeah, if it starts and ends at the same speed, then there's no change in kinetic energy, so the net work has to be 0, right? Work kinetic energy theorem. If it starts and ends at different speeds, then that's not true anymore, right?
Thank you.
Okay. So what we do when I do these problems, I'll tell you how I do it. I find the potential, right? So one point is at lower potential than the other point. Point B is at lower potential than point P. Electric field always points in the direction of lower electric potential. So I know that the electric field is basically pointing from P to B. This is a positive charge. This is a positive charge. I release a positive charge there. What direction does it go? In the direction of the field. So the field is doing positive work, right? It's pushing the particle in the direction it's moving, doing positive work. And an external force would have to reach in and slow it down, reach in, doing negative work on the object.
Professor, I have another question
Yeah.
here. Can we calculate the other way around? Because I just read the question. You say starting with rest and then finish with rest. So the mechanical energy is zero, right? Change over because speed didn't change. So the potential, electrical potential difference is the work has been done to it. For example, if you move from smaller potential to higher potential, it's just like gravity, right? If you move up, and then the speed of the beginning and the end are the same. So the only difference is you increase your potential, gravity potential, you must have external force did some work to it. Can we be using the same concept here? So that way I don't need to keep thinking about where is the direction, the electric force applied to it. I just use the beginning, the total energy, and the difference. Can we
I think the short answer is no, because you're forgetting that that there are two different kinds of charges, right? So you're thinking that if you move something to higher potential, you've increased the potential energy. Well, that's true if it's a positive charge. If it's a negative charge that you're moving to higher potential, you've decreased its potential energy. So
yeah, but if you decrease the potential energy, that means the external work done to it is decreasing. So then it's negative.
yes. Yeah. So yeah, you can think in those terms, sure. Okay.
Thanks.
All right. So E is at the same equipotential surface, is on the same equipotential surface as P. It's at the same potential as P. So how much work? No work is done, correct. Okay, we good? So there's 3 more or 4 more there you can do if you'd like to. We did 3 of them. So think about that, and then change the sign of the charge. So we were moving a positive charge, go back, change it to a negative charge, go through the same questions again using a negative charge. Okay, so let's talk about potential energy a little bit. It's a good lead in there. So if we draw our potential, we've got this 1 over r dependence, right? V is k q over r. That's potential as a function of r. And we know that positive charges want to move to lower potential because that's the direction the electric field points, right? Positive charges want to go to lower potential. Negative charges naturally want to go to higher potential. Some people kind of say that positive charges roll down the potential hill, right? Kind of like a ball would roll down a hill because due to gravity. Negative charges roll uphill, though. If you think of positive charges as going to lower potential, negative charges want to naturally go to higher potential. They roll uphill, if you like that analogy. And if it's a negative charge, then we have this equation, right? And we get this negative 1 over r situation. Okay. But positive charges would still roll down the hill towards lower electric potential, right? Positive charge would go this way, negative charge would go that way. All right, so potential energy. Every time we've come up with a conservative force, we come up with a potential energy term. We talk about potential energy. And so the first one we had was gravity. We came up with gravitational potential energy. There was the spring force was conservative. We did spring potential energy. Now we have an electric force, which is conservative. We saw that, I think, last week. Excuse me. So what we've got is a situation that's a little more complicated, because with gravity, we only had 2 gravitational forces, right? So let's think about gravity. We've got for 9 weeks out of the physics 4a, what was the force of gravity? mg. And so what do? We find the work done by that force, and we set that equal to potential energy, mgy, right? We integrate the force to get the work done, and we get a potential energy term. Well, the last week or so of physics 4a, we said that gravity doesn't just apply when we're at the surface of the Earth, because F equals mg, that only works at the surface of the Earth. We have a universal law of gravity that works between any 2 objects anywhere in space. F is g m1 m2 over r squared. And we integrated that to find the work done in moving an object in that under the influence of that force. And we said the gravitational potential energy is minus g m1 m2 over r. So that was we only had 2 gravitational forces. It couldn't be anything else. Those are the only 2 options we had. And so we came up with a gravitational potential energy term, right, for each one of those. So we know what it is. It's a formula right there. We can look at it and see exactly what the gravitational potential energy has to be. But it's a little more complicated with electric forces, because electric field could be anything, right? Let's look at our electric. We could have E equals a constant, right? If we have an infinite sheet of charge and we're out in front of it, the electric field's uniform everywhere, constant, right? We could have the electric field being proportional to 1 over r. If we're outside of a line charge or a cylindrical charge distribution, the electric field drops off as 1 over r. We could have the electric field dropping off as 1 over r squared, right? If we're outside of a spherical charge distribution. We could have E proportional to r, right? If we're inside of a spherical, we saw earlier today, inside, right? You can see here, I can come up with almost anything, right? So because there's so many, E could be almost any formula for E, depending on how our charges are arranged, then there's almost an equal number of potential energy terms. So there's not one formula we can hang our hat on, one thing that we can go to every time and say, this is the formula for electric potential energy. We don't have that, because it depends. The electric force is always changing, depends on the electric field. The electric field could be almost anything, right? There's no 1 or 2 possibilities. There's a whole bunch of possibilities. So we don't have one formula. So what do we do? How do we get our electric potential energy? Electric. Well, we use the fact that the work done is minus change in potential energy, and the work done is minus Q delta V. That's the work done by the field. There's a minus sign in that equation when it's the work done by the field. And so we use these two equations and we come up with it that way. That's how we get electric potential energy in our situations. So let's think about potential energy for a second. And so if this is the Earth, let's use our analogy here of the Earth and gravity. And I have a mass here. And okay, so if I have a mass close to the surface of the Earth and I let go of it, the force of gravity can act on it for a certain distance, and it'll have some final speed right before it hits the Earth. If I take that same mass and I raise it up higher in the gravitational field, the force of gravity has a much longer distance to act on it now, and it'll be going much faster when it hits the surface of the Earth, right? So it has to have more stored energy when it's higher up. It has to have more potential energy when it's higher up than when it's down low, because it's going to have more speed when it hits the Earth, right? We're all good with that. So I usually think of electric fields and forces with the same thing. I put like I imagine a wall in my problem somewhere. So let's say I had an electric field pointing in this direction. So I have an electric field pointing in this direction, and I have a positive charge here. So sometimes it's hard to imagine, you know, if I give you this situation, I say which charge has more potential energy, which charge field system has more potential energy, the one on the left or the one on the right? Sometimes it's a little hard to see it. So put an imaginary surface in here, put a wall here, and say, okay, I'm going to release the charge that's closer to the wall. What's going to happen? The electric field is going to push it in that direction, and it's going to have a certain speed before it hits the wall right here, right? The other one, if I release the other one, the electric field is going to act on it over a much longer distance, and it's going to have a bigger speed when it hits the wall right there. So it had to have had more stored energy. It had to have had more potential energy. The field particle system had more potential energy when it was at the position on the right than at the left, when it was higher up. And another way to think of it is what would it have taken to get the particle there? If the particle started out here at position 1 and it ended up at position 2, how did it get there? Did the field push it in that direction, or did you have to reach in and push it in that direction with an external force? In this case, if you let go of the particle at position 1, it would go down. It wouldn't go in the other direction. It wouldn't go toward 2 due to the field. So by you coming in and pushing it in the other direction, you're adding some energy to the system. You're increasing the system's potential energy. So 2 has to have more potential energy than 1. So kind of think about things like that. Whatever helps you to figure it out. If I started out at 2 and I moved it to 1, I have to end up with less potential energy because the system the field moves it that way on its own. It's kind of like a spring. If you push a spring together, you have all that stored energy. If you allow the spring to stretch a little bit and go back towards its equilibrium position, you've released some of that energy in the spring. The spring now has less potential energy than it had before. That's what's happening when that positive charge moves from 2 to 1. When it's in position 2, it's like a spring is pressed really tightly, lots of stored energy. You allow it to move to position 1, and you've taken some of that energy out. So there's less stored energy when it's at position 1. So whatever thought process you like, if you like, put the imaginary wall in there and see how fast the particles would be. The one that's faster when it gets to that wall had to have more starting energy, had to have more stored energy, potential energy. Okay, or think about the sign of the work done and getting it from one place to the other, whatever you like to do. Then go through the same process with negative charges and get used to thinking in those terms. Could we use... So where U is 0 is kind of going to depend on where you defined your potential to be 0, I guess, right? Because you've got your change in electric potential energy is linked to delta V. Okay, so one thing we do with potential energy is we think about how much energy it takes to bring charges together, system of charges. So let's just do 3. 3-point charges, Q1, Q2, Q3. And first thing we do is we bring in, all 3 of these charges are at infinity, far away from each other. They're not interacting with each other. And we're going to bring Q1 in from infinity. And there's nothing else there, right? So how much work does it take to do that? Okay, it doesn't take any work. Why doesn't it take any work? Because there's no other charges there, right? There's no other field. These charges are at infinity, far away from each other. We pull one in. There was no electric field to fight against, right, or to help us. So no work was done bringing in that first one. So it has no energy, right? If we didn't have to put any energy into moving it there, then there's no stored energy. We didn't add any energy to the system. We didn't take any energy away. Now we bring in the second one. Now Q1 is there, right? So there's some interaction. As we bring in Q2, it's interacting with Q1. If they're like charges, they repel each other. We have to do some positive work, external work, bringing it in, right? And that means there's going to be some stored energy in the system, kind of like taking a spring and pressing it, compressing it, right? This is some stored energy now. If they're the same charge, then Q2 is attracted to Q1, and we have to do some negative work, slowing it down, preventing it from going in and colliding with Q1, right? So we end up with this situation. What we do is we can find work is done against the field from Q1. So we say Q1 is here, Q2 is there. So we say, what's the potential? The Q2 started at 0 potential, right? Because the potential from a point charge is 0 at infinity. And it came into some other potential. I'll call it V1. And this distance we'll call R12. So we find the potential there. What is that equal to? K Q1 over R12, right? And then we say that the potential energy of this system, the 1-2 system, is charge 2 multiplied by the potential that existed at that location before we brought it there. So there's the potential energy of these two point charges. Now, if we bring in the third charge, and it's doing work against both the fields, right? So we have a Q1, we have a Q2, and now we have a Q3 over here. So this is R23, that's R12. This I'm going to call R13. So there's distances between them. And what is the potential energy? So I end up with and so for the system of all three charges, I'm going to call this U2, not U12, sorry. You get these interactions that occur. You have to sum up every possible interaction. But that's it. For three charges, you end up with this. And for this equation, the trick here is the Q's, where am I here? I'm running out of room. Q's can be positive or negative. Use the correct sign. Because U can be positive or negative. So if your two Q's are both the same sign, then your U is positive, right? You have some positive potential energy in the system when you push two like charges together. But if they're opposite signs, they want to attract, and you actually have a negative potential energy. It's going to take energy to pull them apart. Now, this is after the charges are brought close together. Once we bring the charges in, so Q2 started out at infinity, but we brought it in from infinity. Where did it end up? At R12 here. And we want to know how much energy did it take to bring it in, or how much energy are we going to get out of this system if we let it go back to infinity. So that's potential energy for a system of charges. Sometimes they call that binding energy. It's how much energy it would take to separate the charges out to infinity. Okay, and the one other thing we do with electric potential, we talked about several times. I mentioned that, in, I think one of the first days of class, what did we do? We took two conductors and we said this one had plus 4 at charge, and this one had minus 2, and we touched them together. And what do they have when we touch them together? A total of plus 2, which splits 50-50, right? Half and half. And then if we separate them, we have a plus 1 and a plus 1, right? Well, that's only true if these conductive spheres are identical or the same radius. Okay, so we're going to learn now why that doesn't have to be true if they're different radii. Okay, so here we have okay, so we've got these three conductors, and we are going to connect them with wires. Okay, so connect. So the question is, what's the charge on each one of these after we connect them with wires? Okay, so let's find those charges. Well, what is different now than when we first learned this on the first day is that we know about electric potential now. And when you take these conductive surfaces and touch them together, you're creating one big conductive surface. And one thing we know about a conductor in electrostatic equilibrium is V has to be a constant. It has to be an equipotential surface. So the potential of each one of these has to be the same. And what is the potential on the surface of a spherical charge distribution? We did it earlier today. We treat it like a point charge, right? So the potential of a point charge is KQ over R. And we just plug in the radius of that object. So in this case, it would just be capital R. And this would be KQ2 over 2R, right? And this would be, oops, not plus, equals KQ3 over 3R. So this tells us that the potential has to be the same on each one of those surfaces. So where the radius gets smaller, it turns out the charge density increases. The charge also gets smaller, but because the surface area increases faster or gets smaller faster than at a higher rate than the charge does, the density, surface charge density actually increases. So what we end up with, so these are some of our equations, right? So with this, and What else do we know? The total charge has to be the same. The charge couldn't just disappear, right, or appear. Whatever charge we started with, we have to end up with the same charge at the end. So it has to be 9Q total charge. Okay? So if you go through and do this, I'll let you do some algebra. But what you end up with is Q for the 1R radius is 3/2 of Q, and Q2 is twice as much, which is 3Q, and Q3 is 3 times Q1, which is 9/2. So you can go through and check that later. But that's the reason. So when the radii are the same, the charge splits equally. But when they're different, the potential has to be the same on all those surfaces, and the charge distributes to make them an equipotential surface. Okay, so we will stop here. I'll see if you have any questions. I'll stop the recording, and then we'll continue next time.